Good afternoon, everybody. Welcome to Monday afternoon. Cloudy, and it looks like it's going to be rainy around my house. A Monday afternoon at Chem 170 with your host, me, Dr. White. Hi. All right, a couple things before we get started. First of all, today I started teaching at the other school I teach at, College of DuPage. Sorry about that. And on Tuesday and Thursdays, which will be tomorrow, which didn't happen last week, I finish about 10 to 1 in DuPage. I've got to get home for here for 2 o'clock. Now, usually that's enough time. I have no problem. But if there's bad weather, accident on 355, whatever, I might, on a rare occasion, hopefully never, be late. Hang in there. You can log in early. I don't think I'll ever be more than 15 minutes late. I hope I'm never late. But anyways, on Tuesday and Monday and Wednesday, I finish a lot earlier because it's a lab, not a long lecture. The way they have it set up, they have a 3-hour lab. Their lab is scheduled longer than ECC for the same kind of course on Monday and Wednesday. And on Tuesday and Thursday, they have 4 hours of lecture. I've done it before. It's grueling, but then again, my students like you are worth it. All right, so I just wanted you to be aware of that. Now, another thing, some of your colleagues have already asked either by email or earlier today by chat about, I posted the first lab scores on D2L. Unfortunately, I don't really have an easy way to mark what was wrong. If you want to know, come to my office hour or email me. I'll be more than happy to tell you. As I've always said, there's no such thing as a dumb question. Excuse me, and that applies to anything I grade of yours. You should always feel comfortable asking, why did I get the score? All right, now, here's today's lecture. A couple of things, game plan for today. As promised, as soon as I'm through talking now, I'll go through the alkenes, alkynes problem set. Next, new chapter time, new functional group. And then I think I'll end the actual lecture part of today's lecture about 10 minutes early. Instead of 4:40, I'll stop at 4:30, and from 4:30 till I finish, about 10, 12 minutes, I will be doing teaching for those who want to stick around. It's optional. My method that eliminates test anxiety like that. It works real good. I've been teaching it a number of years. I've seen students go from D's, F's, D's, or C's up to B's and A's, not only in my class, other classes. That will be cut out of the video, but I will be doing that today. For those who can't make it to the video, come to my office hour or email me and I'll set up some time when I can teach you that. All right, before we get going, any questions? Well, I guess not. So I better get to work. All right, thumbs up, people. I haven't done this in a while. Did everybody see the alkenes problem set? Thank you. All right. Now, after test number 1, you'll understand why I call these a problem set. Let me just make this a little smaller. All right. Now, on test number 1, there'll be 2 types of nomenclature questions. Nomenclature is naming. And the first one is give the Iupac name for the following. How do you do that? Well, you look for what's different. And let's look at C. If I don't do one you'd like me to do, ask, please. All right, we look at C. from now through the rest of the semester, whenever you look at an organic molecule, you should look for what's different. What's not a carbon-carbon single bond or a carbon or hydrogen atom should attract your attention like that did. And if we look at, say, a double bond, and this is an alkene, how many carbons in the longest chain of a double bond? Well, even though this is bent, this carbon is bonded to this carbon, this. And that's 5 carbons. And hopefully you've learned 5 carbons is pentane. Well, for a double bond alkene, take the alkane name, pentane, drop the A-N-E, put E-N-E, pentane. Next, what's the lead carbon of the double bond that's close to one end of the chain? And that should always have the lowest number. And notice if I start from here, that lead carbon is on carbon 2. If I start from the other one, it would be 3. And now you have to use your high-level math skills, which is smaller number, 2 or 3. And the answer is 2. So that's 2 pentane. Now, if you notice on each carbon of the double bond, you have a hydrogen. And now we have to consider, is this cis or trans? And remember, cis is same side of the 2 atoms, the same on each carbon or groups. This class will be hydrogen. And trans is opposite side. And what we're talking about, we have a double bond, we're showing stereochemistry, the bond angles. You have a line or plane, and if they're both below, that's cis. If one's here and one's here, opposite sides, that's trans. If you notice, the 2 hydrogens are on the same side, so that's cis, and that's cis-2-pentene. Now, if we look at B, we have, oh, a ring. Dr. White, Mother Nature, love rings. Well, we got a double bond in there. And therefore, how many carbons in the ring? 6. Cyclohexane. Don't forget, common mistake on test number 1 is for ring, students forget to put the cyclo. Well, that's got a double bond, so the A-N-E ending, cyclohexane, becomes cyclohexene. Now, when you only have one double bond in a ring, which is what's going to happen in my class, don't tell anybody I gave it away. But anyways, one of the carbons of double bond will always be 1, the other will be 2. You do it in such a way that the alkyl groups also have the lowest numbering. Now, here we have cyclohexene. Because one's going to be 1, the other 2, you don't have to put a number where the double bond is. Also, notice it's always going to be cis in rings I talk about. So you don't have to say it's cis. Now, we have a methyl group and an ethyl group. And hopefully by now you've learned the alkyl groups from the table in the lecture section. Now, how do you number this? So one carbon is 1, the other is 2, and it has the lowest numbers. Well, if this carbon is 1, the methyl group is on 1, the ethyl group is on 3. Now, common mistake students make they say, I'm going to make this 1, I'm going to make this 2. and somehow they try and make that 3. No, if you call this 1, this 2, you have to keep on numbering 3, 4, 5, 6. And notice this is on this carbon here. This numbering is 6, and that can't happen because one of the carbons double bond has to be 1, the other has to be 2. Now, another way, which would also be wrong, if I make this 1, the methyl group is on 2, 3, 4, 5, 6. That way you have either 1, 3 or 2, 6, which are smaller numbers. I'll pick 1, 3. And that's why it's numbered. Now, remember, I am not going to, don't tell anybody I'm saying this, I'm not going to hold you to the alphabetical order of the Iupac rules for substituents, alkyl groups. So if you had put down 1-methyl, 3-ethyl cyclohexane, I'll give you full credit. Now, let's look at D. And you say, all right, how many carbons in the longest chain? It doesn't matter which methyl group here or here, 1, 2, 3, 4, 5. That's pentane. Double bond, drop the A and E ending, put ENE, pentene. This is carbon 1, the double bond starts at 2. And notice on 2, you also have this methyl group. Now, that would be also on carbon 2, so it's 2-methyl, 2-pentane. And the question is, what about cis and trans? Well, if you look here, notice here's a hydrogen. It's on the same side as the methyl group. That's cis, but it's on the same opposite side of that methyl group. That's trans. Well, which is it? It's neither. When you have 2 of the same atom or substituent or group on, one of the carbons a double bond, it cannot be cis or trans. And here's another example. Similar, one of the bonds has to be 1, the other has 2 to give the alkyl group the lowest numbers, and that's the way you do it. All right, there are 2 types of nomenclature, naming questions on my test, and also naming or nomenclature skills people who use organic chemistry should have. And the second one is draw the condensed structure for the following Iupac names. And here, how do we do that? You start with the right and you move left. ENE ending, double bond. There were ANE, cyclohexane ring with double bond. Now I put mine here. You can put it between any 2 carbons because all you're doing is rotating the ring. Now let's go to C and have some fun. And how do you decode this to know what to draw? You start from the right, move left. ENE ending, double bond. If that were ANE, octane, hopefully you've learned this, hint, 8 carbons. So I have, where's the double bond? Starting at carbon 3. 1, 2, 3. Notice it's trans, so the hydrogens are on opposite sides. 4, 5, 6, 7, 8. Ooh, methyl, you know that. And di means 2, tri means 3. That's di. That means there are 2 methyl groups. And where are they? On carbons 5 and 6. One thing, if you look on D, in the past, students have wanted to do, since I'm already do part of the line for ring, all of it, and that's fine by me. So that's why I started drawing both of these down. All right, now on test 1, and sometime this week, I'll be posting information about test number 1, how many pages, how many problems, and I will also have a breakdown. And for test 1, I call it general information, nomenclature, and reactions. This is a reaction problem. Now here, the question is, give the organic reaction product or products for the following. How do you do this? You look for what's different. What's not a carbon-carbon single bond or carbon or hydrogen atom should get your attention like this. I love this. And if we look at A, what do we have? Double bond. And what are we reacting with? Hydrogen and nickel. And the general reaction, any double bond reacts with hydrogen and a catalyst. Oops, I forgot to put down, bad Dr. White. Catalyst can be nickel, platinum, or palladium. And you break the pi bond. Remember, double bond has one pi bond, one sigma bond, and each carbon of the double bond gets a hydrogen. Now, do you break carbon-carbon single bond, sigma bond? No. Let me say that again, slow motion. Do you break carbon-carbon single bonds? No. So don't. It was amazing. Once I started brainwashing all the students, which I'm doing now to you, the test scores really zoomed up. Students did the craziest things before I started saying that. I mean, crazy. That's not what I want. That's what I want. Now, if you notice in B, same thing, different catalyst, double bond. On a ring, you don't show hydrogens. So I broke the pi bond, but I don't show the hydrogens. You look at, say, the bottom carbon here, it has 3 bonds. Another thing you should remember, there's always 4. Yes, 4 bonds to carbon. And this has 1 hydrogen. When you add the hydrogen, this now has 2. So you have added hydrogen to each carbon double bond. Now, another reaction is halogenation. I did it again, bad Dr. White. And here we're reacting what's different, double bond. And here, what do we have? Halogen. You break, remember X we use in organic chemistry for halogen. This could be fluorine, chlorine, bromine, or iodine. In fact, let me do something real quick. Here's what I forgot to write. And this is a general reaction, which I'm going to be honest, you need to know and memorize for test 1 and the final. And you break the pi bond, each carbon double bond gets the halogen. Do you break carbon-carbon single bonds? No. So I started with 3, I end up with 3. And the 2 carbons with the halogen of the double bond get the halogen. In this case, it's chlorine. Now, D is the chemistry instructor's favorite trick on a test, mine included. That's put a big, scary molecule. It's only big and scary if you don't know to look for a double bond. And once I see bromine gas, Br2, double bond, think of this reaction. Do you break carbon-carbon single bonds? No. So I have 1, 2, 3, 4, 5, 6 across. I have my 2 methyls. Here are my 2 carbons, double bond. Each one of those gets a halogen, bromine. Now, next one, I have a double bond. I'm reacting with HBr. Well, that's HX. And this one, I've never seen anybody use it with fluorine, so that's why I'm leaving it out. And this follows Markov-Nikols's rule, which is the carbon of the double bond with the most hydrogens gets the H, the other carbon gets the X. And if you get that wrong, you get 0 points, because that's what I'm testing, your knowledge of Markov-Nikols's rule. And if we look at E, double bond, one side has 2 hydrogens, the other 1. Using your high-level math skills, I hope you all know 2 is greater than 1. The H goes here. The halogen goes there. Do you break carbon-carbon single bonds? No. So I have 1, 2, 3, 1, 2, 3, and that's how you get it. Now, as I mentioned in class, Mother Nature and Dr. White love rings. Students don't. And here's why. Ooh, what's different? Double bond, HI, which is this HX. Therefore, one carbon to double bond gets H, the other gets X. But now you have to figure out how many hydrogens on each carbon to double bond the ring. Or remember, there's four bonds to carbon. And if I count this bottom carbon of the double bond, I see 1, 2, plus the double bond is 2 more, that's 4. 4 minus 4 is 0. If I go to the top carbon, 1, 2, 3. 4 minus 3 is 1. So which is bigger, 1 or 0? And time's up, 1. So the H goes here, and the halogen goes here. The isopropyl state comes along for the ride. And this is how you draw it, because you don't show hydrogens on a ring. Now, let's continue. What do we have? Double bond. Remember, look for what's different. What's not a carbon-carbon single bond or carbon or hydrogen should get your attention like that. Oh, that was feeble. That's better. Anyways, double bond, H plus means acid catalyst. H plus means acid catalyst. And water, H2O. And think of water as HOH, OH hydroxyl group. And you break the pi bond, one carbon gets H, the other gets the OH, and it follows Markov-Nikols's rule. The carbon with the most hydrogens gets the H, and the other carbon gets the hydroxyl group OH. And if we look at this molecule right here, G, 2 on this carbon, 1 on that carbon, the double bond, which is the larger number. Hopefully you pick 2. So the hydrogen goes on the end, and the hydroxyl from the water goes in the middle. Oh, I got it right. Now, if we look at H, same thing again. You got to figure out the hydrogens. The bottom carbon double bond has 0, top 1. Therefore, the hydrogen from water goes up here. The hydroxyl group goes down here. Now, if you switch the methyl and the hydroxyl group, so this is over here and this, that's okay. All right, before I move on, any questions on double bonds? Going once, going twice. Okay. Ooh, I got a question for you. How many of you drove by, let me go into speaker view or gallery view. How many of you drove by a gas station, thought about half the weight of gasoline, they're selling alkanes? Anybody? Oh, I see one. How many of you happen to think if you're barbecuing or you're at a barbecue this weekend or during the week too, that the propane is an alkane? Anybody use baby oil, Vaseline? Think about those have alkanes? How about looking at a candle and thinking about half the weight of the candle is alkanes? All right. Thank you, Alex. Now, remember, organic chemistry is all around you. I stole that from SpongeBob, and it won't hurt you to think about it outside my class. So remember, if you're going by a gas station, they're selling alkanes. If you happen to use a barbecue, the propane is an alkane. And also your cooking gas, natural gas, that also heats up the water in your house. I don't think today you'll need your heater, I hope not, to heat up your house. Air conditioner, yes, heater, no. See, Alex, organic chemistry is fun, at least for Dr. White and hopefully for you. All right, let's continue on. Let's talk about the next section of the problem set, and that's alkynes. And the first question is, give the Iupac name. Now, if you look at A, I told you the common name is acetylene, which I asked you to learn. If I give you a common name, it's dry. But for this, I'm asking for the Iupac name. I'm being sneaky. And that's ethyne, triple bond. Find the longest chain, name it as an alkane, and then you drop the ANE ending and put YNE. Now, this is the only one. There's no way you can have two ethyne. Since everybody knows that, that's why I don't have one ethyne. Now, if we look at, let's look at C. What's different? Oh, a triple bond. How many carbons in the longest chain containing both carbons of the double bond? Well, we do 1, 2, 3, 4, 5, 6, 7. 7 is heptane, but since I have a triple, did I say double bond? I do that sometimes. Since we have a triple bond, drop the ANE ending and use YNE, heptine. Which carbon is the triple bond carbon closest to? This way, 1, 2, 3. This way, 1, 2, 3, 4. So 3 is less than 4. That's 3 heptine. Oh, look, it's your old friend, the methyl group, and it's on carbon 2. That's how you get 2-methyl-3-heptine. Now, this one I wrote to trick you. How many people, and you don't have to raise your hand, put down T-butyl group in the name somewhere? Well, this was designed, there's the T. No, what's the longest chain? 1, 2, 3, 4, 5, 6. Has a triple bond. Hexane, 6 carbons. Triple bond. YNE ending, you drop the ANE, put in YNE, hexine. What's the carbon of the triple bond? I want to say double bonds. I don't know. I think I got double bonds on the brain today. Hold on. Where's my reboot switch? All right. What's the end of the triple bond that's closest to the end of the chain and at the same time gives the alkyl group's lowest numbers? We start here, side carbon 2, 3, and the substituents, 2 methyl groups, are on 2. We do the other way, it's 3, 2, but the methyl groups would be on 5. That's why this is the correct way. So we have 2 methyl groups. 2, we use the prefix di, and whenever you use di, you need 2 numbers, even if they're on the same carbon. And therefore, it's 2,2-dimethyl-3-hexine. And you don't have rings in with a triple bond, at least in my class. In real life, I think I saw one a couple of decades ago in a paper, but I haven't ever since. I also haven't been looking for it. But anyways, draw the condensed structure, and I should say for the Iupac or common names of the following molecules. Acetylene, this is one way of drawing it. and this is the other way. Either way is correct. And that's not what I want. All right, now let's look at C. How do you draw this? Well, you start from the right and move left. Why any ending? Triple bond. Heptane would be 7 carbons. So we have 7 carbons with a triple bond. Where does the triple bond start? Carbon 3. So most are going to start from this end. Could have also started from the other end. 1, 2, 3. There's my triple bond. Then, methyl, I know that's CH3. Diamines, there are 2 of them. And where are they? On carbon 2 and 5. If you label this 3 and that 4, this has to be 2, this has to be 5. There's the methyl groups. All right, let's look at some chemistry. And on test number 1, I will have reactions. And the answer would be give the organic reaction product or products of the following reaction. And what do we do? Look for what's different in a molecule. What's not a carbon-carbon single bond or carbon-hydrogen. Just get your attention like that. Oh, wait, that's better. Let's go for it. Like that. That works real good. So what's different? Triple bond, hydrogen excess. I forgot to put the catalyst. Bad Dr. White. I put it in the problem set answers. But anyways, hydrogen excess, and this bracket X, letter S, closed bracket, means you have all the hydrogen in the world with anything that will react with hydrogen. In this case, triple bond. You break the 2 pi bonds. Remember, triple bond has 2 pi bonds. And a triple bond has 2 pi bonds and 1 sigma bond. And each carbon of the triple bond gets 2 hydrogens. So if I break here, you break carbon-carbon single bonds. Now I started with 3, I end up with 3. It broke the 2 pi bonds, and each carbon of the triple bond gets 2 hydrogens. And if we look at B, again, big scary molecule. No, you got to look for what's different. And here we have a triple bond, hydrogen excess. Again, I forgot in the first problem set, or the empty one, to put the catalyst, but I did here. And you break 2 pi bonds, and each carbon of the triple bond gets a hydrogen. Notice we have 1, 2, 3, 4, 5, 6 cross atom, methyl here and here, dimethyl, and it's still there, and that's what happens. Now, for C and D, and let's look at D. What's different? Triple bond. What are we reacting with? Halogen gas. In this case, I remember to put X can be chlorine, bromine, fluorine, and iodine. And we have excess, so we don't have to balance the chemical equation. And you break 2 pi bonds, and each carbon of the triple bond gets 2 halogens because of that. So here they are. You break carbon-carbon single bonds? No. So I have 1, 2, 3, 4, 5, 6 across. On this carbon, I have 2 methyls. I did that. And I broke the 2 pi bonds, and each carbon of the triple bond gets 2 halogens. And we're done. Any questions about alkynes? Oh, I forgot to ask something about alkenes. Anybody happen to look at a carrot or a tomato and think, wow, the color of that is either orange carrot, red tomato, because of molecule with a lot of double bonds. Anybody do that? I'm not going to give up. I got the whole summer almost to work on you people to think about things like that. All right, any questions, triple bonds? All right, it's new functional group time. Wow. Let me close something up here. Oh, excuse me. And the new chapter is aromatic compounds. And I should tell you, wars have been fought, yes, wars over aromatic compounds. And our world has changed because of aromatic compounds. Aromatic compounds were named that because they were originally organic compounds isolated, meaning extracted from spices and vanillin. And they're found to have unusual characteristics and stability. And they have a ring, all of them, C6H something. I have 6 here, it can also be H5. Sorry about that. I was thinking about what I was going to say. All right, now, some of these compounds, I had a rough night, sorry. But anyways, some of these compounds came from spices and herbs, such as vanilla. And they have, like I said, unusual chemical properties, especially stability. They don't change with time and air. And many of them have a C6, and really it should be H5 ring. Oops, that's not what I want. Wow. Now, when I start teaching this, there's a great book after the summer class you should read. And it's called Napoleon's Buttons. And it's about time for me to read it again. Good books, I go back like good friends you like to visit. I like to go back and visit good books. And let's see if I can find it for you. And you get it everywhere. I'll pull up Amazon, even though I don't get any. And here's the book called Napoleon's Buttons. And I don't get any kickbacks, but this is about 17 groups of molecules that have influenced the history of our planet. And they did a great job of talking about these molecules, and most of them are organic. Now, why is this book called Napoleon's Buttons? Well, there's I don't know if you call it a wives' tale or a myth, and nobody knows if it's true or not. When Napoleon attacked Russia, and they had a brutal winter when they were fighting, and Napoleon lost, partly because of the weather, the myth goes, what helped them lose? Well, their buttons were made out of a cheap metal that the super cold temperatures that winter in Russia became what chemists call friable. They broke apart. If you're trying to fight in a war and it's brutal cold out, and your buttons of your coat and your pants broke, you're having trouble before you even start in a battle. And that happened, but there's enough evidence that it might have. And that's why they called their book Napoleon's Buttons. Now, one area they talk about were aromatic compounds. And aromatic compounds, wars have been fought in the 14th, 15th, 16th, 17th centuries over them, or more specifically, places where you can grow them, things to make them, those aromatic compounds, spices and herbs. If you think about it, the United States was discovered, if you believe Columbus was first, or if you think about it, were the Vikings here first, but let's go with the Columbus first right now. What was he doing? So he found America, but he wasn't looking for America. He was looking for a shorter route to get to India and that part of the world to be able to buy spices, bring them back to Europe and make money. So these aromatic compounds are very important in our daily life. And why were they so important back then? And this is Dr. White's theory, and I might be totally wrong, but if you think about the 1400s, 1500s, 1600s, and 1700s, they didn't have refrigeration. So if you cook something like meat, later on it started going funky on you. And how could you make it better before it went too funky? Put a lot of spice on it. And they did. They also found a way of preserving meat, but that's another class, not this. Now, when we talk about benzene, and that's the simplest of all aromatic compounds, any organic chemist will immediately think of the great German, or maybe that was Austrian at that time, German chemist Kekule. By the way, switches off on this slide. Same thing for the previous one. And Kekule is one of the greatest organic chemists. What made Kekule great? Well, he was the first one to propose a reasonable structure for benzene. Now, benzene is the simplest aromatic compound, has 6 hydrogens and 6 carbons, 6 and 6, and it's in a ring. Well, how do you draw that? Well, Kekule came up with that idea. Now, that alone, coming up with the proposed reasonable structure, which was a correct one for benzene, that alone is a lifetime achievement. But he did a few other things too, like I'll tell you about his snake dream that all organic chemists know, if they're good organic chemists. And he was the first one to recognize that carbon should have 4 bonds to it. We call that the tetravalence, but I always say 4 bonds to carbon. That was Kekule. He was the first one to recognize, this is a long time ago, carbon atoms can be connected together by chemical bonds. And what he really, in his structure of benzene, developed that it contains 3 conjugated double bonds. Conjugated double bonds means alternating single, double, single, double, single, double. Those are all lifetime achievements for any one person, and he did these all. Now, this is from a country that no longer exists, which issued a postcard. Don't you love his beard? I wish I could have one of those again. I didn't have the V in mind, but since I might have to put on a gas mask when I visit a chemical plant, I got to keep my beard short. But here's Kekule. He lived from 1829 to 1896. And about 1830s, 1840 is when he made his great discoveries, a number of them. And this is from DDR, which is Deutsches Democratic Republic, otherwise known as East Germany, which is long gone, thank goodness. This was issued in 79, and this is 25 Deutsche Mark. And a number of years ago, I was telling students, if you see this, let me know. If you see it anywhere for sale, if it's reasonable, I'll buy one or two. Well, about 3 years ago, one of my students taking Chem 170 emailed me and said, guess what I found on eBay? That stamp. And it was pretty cheap, so I now am the proud owner of two of these. All right, right here over his shoulder, that's the structure of benzene he proposed, which was correct. Now, I should mention, do I have time? Hold on. I do. What's this Kekulé snake dream? And when he was older, like you see in the stamp, he was at a seminar, he was talking about his discoveries, and someone asked him the question, Dr. Kekulé, I'm sure he had a PhD, I think he does, or did. How did you come up with the idea of benzene, the structure for it? And the story he told was, the night before, I had this strange dream. And the dream was a snake was going around in a circle trying to catch its tail. And it did. It caught its tail. So it was going around in a circle, its head holding on to its tail. And that gave me the idea for benzene. And that's Kekulé's snake dream. I'll never ask that on test, but I thought that would be something you should know. Now, Kekulé's model I have here for benzene shows what's called resonance structures or models. Resonance is when between two molecules, you change where the electrons are, atoms don't move. And you show that by a double-headed arrow. Now, when I did this a number of years ago, I got over gung-ho. I put it in brackets. You don't really need brackets. And that says neither one of these are really isolated. It exists at both at the same time, which is why we have the double-headed arrow. And if I take this bond right here, double bond the pi electrons and move them over here, this one has to move down here. This one has to move over there. You'd have too many bonds to carbon. Well, when you do that, you get this molecule. And if this moves, and this moves, and this, it goes back to here. So it's going back and forth. Speaking about back and forth, I just noticed it's time for our break. Come back at 2:55 and we'll continue on. I'll see you all in 5 minutes. I'm gonna get up and stretch. Let's get going. All right, before I continue, two public service announcements from the management, me, Dr. White. Number one, what was that? Anyways, number one, tonight at 6 p.m., I'll be having on Zoom my office hour, and also have it on Wednesday too. If you have any questions with anything concerned with this course, stop by. I will help. That's why I have my office hours. Technically, in the summer, faculty don't have to have office hours, but they help students, so that's why I'm having them in the summer even. All right, the other one, this is a personal public service announcement, and that is coming up soon. I'm not sure the exact date, is in Illinois, and I think all of you are in Illinois, and that is the primary. And primary elections are important because that's where they choose each member party who's going to run for positions. And that's important, as important as the November election. And brave men and women have died so you can vote. Make sure if you're old enough, you should be registered. Please vote. All right, back to aromatic compounds. I should mention my favorite aromatic compound is vanillin, like in vanilla extract. I don't know if I mentioned this, but one of the best places to buy spices in the United States is one place located in Evanston. Another of their stores are located in Chicago. I used to go to the Evanston, but with the pandemic and everything, I just have them ship it to me. And everybody see the pure vanilla extract on your screen? Thumbs up, people. All right, this is what I buy from them. I also buy other spices I'll talk about. The stuff is not cheap. 4 ounces is $42. It's gone up in a while. An 8-ounce bottle, usually I'll buy 8-ounce bottle. I splurge, and it'll last a long time because it's aromatic, it's stable. And once you've used this, you'll never buy the garbage they sell in the supermarkets. It's truly, this stuff is that good. And I had to say this, Dr. White is a vanilla extract fanatic, and I love it in a lot of things. All right, we were talking about benzene. And I had the brackets here. You don't really need them now. And double head arrow on the switch off for this slide shows what we call resonance form, how two molecules or forms of a molecule exist by just moving electrons, only electrons. Now, next couple of slides, click, will this be on its test? The answer is no. Now, there are different orbitals. Orbitals, if I could stop time, oh, I wish I could do that. Why, I'd be all powerful. Stop everything from moving. That's where you'd find certain electrons on an atom of a carbon, in this case, carbon atom, involved in certain types of bonding. Now, the p orbital of a carbon atom is in a conjugated double bond overlapped to form what we call pi orbitals, which we talked about with double bonds. And that in a ring, we have this cloud above and below. I'm going to show you pictures. Now, unlike cyclohexane, which is not straight, looks like a boat or a chair, benzene is flat, like a piece of paper, flat paper. Now, this again switches off. Here, each carbon in a six-membered ring has an electron. If this carbon share, that's a double bond. That's the p orbital, pi orbital, or pi bond with the p orbitals. And turns out they can all share their 6 electrons, and it really looks like this in real life. And that's one way of drawing benzene. And think of it. How many of you ever seen little children holding hands and playing Ring Around the Rosie? Well, I haven't thought of that in a long time. And that's what the p orbitals do to make the pi bonds in benzene. No, they don't sing the song. Ooh, that was awful. Sorry. Now, switch is still off, but certain entrance exams talk about this. So I put it in. How do you know if a ring system, and it's got to be a ring system, is aromatic? And we can have all carbons in a ring or carbons in other atoms, and I'll teach you that later in the semester. And the answer is, if the formula 2n plus 2 equals the number of pi conjugated electrons, each pi bond has 2 electrons, then it's aromatic. And again, switch is off. So if we look at benzene, there are 3 ways of drawing it. Here are the 2 resonance forms, and then those are called Kekula structures named after Kekula. And you can also put a circle in, like if you're looking on the top down of the pi cloud, holding hands, looks like a donut. Now, let's call this A, B, C. Any one of those, if I asked you to draw the structure of benzene, would be correct. I think A and B just look cooler, so that's what I'm going to always use in this class. But C is also correct, so if you ever put that on a test, I'll mark it correct, but I just think A and B look cooler. Don't ask me why, but I just showing the bonds makes it look cooler. And Dr. White always tries to be a cool dude. All right, let's talk about benzene. You notice I showed this looks nicer because I used my software. This is how you draw the structure of benzene. So if I ask on a test, draw the structure of benzene, you can use the Kekula structure, either resonance form, what this is called with the circle in there. And this is a larger circle my software does. You can do a smaller one. It's called delocalized pi cloud structure. So once again, now click, the switch is on. If I ask you draw the structure, and you should know this is the structure of benzene. You can either put A, B, or C. Notice for A and B, you have a double bond alternating with a single bond, double bond, single bond, double bond, single bond. And same thing here, you just have the circle. So if I ask for benzene, draw the structure, that's what it is. Now, pay attention. Common mistake on test number 1. If I were to ask, draw the structure of benzene, a student will do this. That's wrong. It's cyclohexane. Don't forget to either put the bonds or the circle inside. So this would be 1, double, single, double, single, double. Or you could have done it the other way. Double, single, double, single, double. Or you could have used the delocalized pie cloud like that. I like the top two. I think they're cooler, but now it's no longer wrong. Don't forget to put the stuff inside. A couple years ago, I had a student on test number 1 for both that and the reactions, forgot to put those in there. That student lost 12 points that they shouldn't have. And the student was quite upset, not with me, more with the student themselves, because that was just a bad mistake that they shouldn't have made. So I'm telling you, common mistake on test number 1, when you're drawing benzene or aromatic compounds, you forget to put the circle or the double bonds in there. Don't. I like that. Don't. All right, let's talk about the nomenclature of aromatic compounds. Now, it turns out benzene has been a name that's been used for eons by organic chemists, or even before they called organic chemists chemists, or even probably called chemists chemists. And Iupac, in their infinite wisdom, and I mean this sincerely, said, you know, we're not going to change chemists calling it something else, and let's keep that name as the Iupac name. So here's benzene. It's not cyclohexene triene or cyclohexatriene, tri-3-ene double bond. Nope, 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 no. This is benzene. Now, as I showed you, there's 3 ways to draw it. This cecula, this other resonance form, which I normally draw, or the delocalized pi bond. This is benzene. Now, another molecule you should know the name of and structure is when you have a benzene ring with a methyl group, CH3, that's called toluene. It's not methylbenzene. No, toluene has been around almost as long the name as benzene. And that's a methyl group with a benzene ring. Now, how do you draw toluene? Like this. You could have shown the other resonance form. Notice that this is 1 and this is 2. Here, there's no double bond between 1 and 2. Here there is. And again, alternating double, single, and so on. And if you don't want to do the bonds, you can do the delocalized. And this is toluene. Now, I should mention in this class, I'll be doing real world stuff teaching you. Benzene and toluene are dangerous substances. Really? Well, besides being flammable, benzene and toluene have serious negative effects on organs in your body and your brain. Very serious effects. Now, back in the 1920s, 30s, and 40s, into the 50s, before they had latex paint, maybe into the 60s, paint was a pigment suspended in benzene or toluene. That would evaporate off, and let's see, where am I? Right there. The wall, this is not that kind of, this is a latex, I'll teach you later. The paint would be, yep, it's dry. But anyways, both of those compounds, when a human inhales them, has serious negative effects on a person's body. And when I was, I don't know, 12 or so, we had one of my mother's, I think 3rd cousins, I can't even remember his name, unfortunately, had been a painter all his life. And this is back in the 30s, 40s, and 50s. And because of that, he was in rooms filled with vapor from benzene or toluene, and it destroyed his brain. At that point, he was not much there. He was about 2 steps of sad above a vegetable, but he was still living. But that was because of the hazardous effects of benzene toluene. What I'm going to tell you, don't use it. How many of you have ever heard about the negative effects of people who sniff glue? And that's very detrimental to their body and brain also. And what's the key thing in glue that gets someone off when they smell it and sniff it? Toluene or benzene. It's dangerous stuff, but at the same time, when handled safely to make things, it's very important. In fact, my last patent I used, and the company I used benzene a lot. I reacted it to make compounds that I'll talk about later in the semester. You got to hang out around here to find out. Oh, a cliffhanger. Now, this compound switches off. I won't ask, but when you have a double bond on a benzene ring, it has the name styrene. And I'll teach you later in the semester a polymer, a material made from this is called polystyrene. And when you make a foam out of that, you know, the insulated white cups with hot stuff in it or cold you can get from various places like McDonald's with your coffee, that's made from styrene. That's why it's called polystyrene. And how many of you are familiar with the very inexpensive, lightweight, white coolers that are super inexpensive and also fall apart easily if you're not careful? That's made with this molecule, and that's called polystyrene foam, and it's made from styrene. But this I won't have on test. All right, let's talk about, you can use numbers to show the location of two or more groups on a benzene or toluene where you have the ring. But in real life, most organic chemists use special names. And those special names are ortho, meta, and para. And these are used for di-2 substitution isomers. And for my class, switches on, better yet, there was a dial that only went to 10, like on an amplifier. I've just turned it up to 20 for this slide. Yep. Oh, I stole that from This is Spinal Tap. And it's an interesting movie if you haven't seen it. It's a cult movie now. But anyways, there's ortho, meta, and para. So I better get to work. And if we were in a classroom, you'd have to be patient watching me do the following, which I have done in the past. All right, here I have three isomers. Isomers are molecules that differ only in the placement of the atoms. They have the same number of atoms and the same type. Now, for compound A, we have a benzene ring. You have an alkyl groups, and you know how to do this. This is ethyl, this is N-propyl. So this would be ethyl, N-propyl, benzene. But I'm not done with this name, and you'll see. And the second one would also be ethyl, N-propyl, benzene. Oh, I forgot an E up there. And the third one would be ethyl and propyl benzene. Well, how do we differentiate? As I've mentioned once or twice, or maybe even 3 times before, no different molecules ever have the same name. We could use numbers, but in aromatic compounds, one of these days I'll do a chart, but I do this on the whiteboard in a classroom. I can do it here. Now, in the first column, we have name, and I'll have ortho, meta, and para. In the second column, ortho is 1,2 disubstituted. Disub is short for disubstituted. Meta is 1,3, and para is 1,4. So instead of using numbers, when you have 1,2 disubstituted benzene ring, we call that ortho. And if this is 1, this is 2. So the first one is called ortho ethyl and propyl benzene. Now the second one, if I call this carbon 1, this would be 2, this would be 3. 1,3 disubstituted is meta. So this would be meta ethyl and propyl benzene. And the final one of my example, we have 1, 2, 3, 4. This is 1,4 disubstituted. If you notice, 1,4 is para. So the top one is orthoethyl and propyl benzene. Say that 5 times quickly. No, you don't have to. Second one is meta-ethyl and propyl benzene. And the last one is para-ethyl and propyl benzene. And you need to know that for aromatic, not cyclohexane, there we only use numbers. How this evolved, I've never really found out. But then again, honestly, I haven't looked that hard either. There's ortho 1,2 disubstituted. Meta 1,3 disubstituted. And para 1,4 disubstituted. And that's how you use it. Now, interesting enough, and let's see what if when you look at toluene, the methyl group is considered a substituent when you're naming it, even though it's included in there. So if I had this, notice this is 1,2 disubstituted methyl group, even though it's in toluene. So first of all, this is ethyl toluene. And it's 1,2 disubstituted. Oh, look, someone was nice enough to put on here 1,2 disubstituted is ortho. So this would be ortho ethyl toluene. Again, even though the methyl is part of the name toluene, that's considered a disubstituted benzene ring, which it is. Oh, I got a question for you. How many of you have ever heard of the pharmaceutical company called Ortho? Boy, you people live the shelter life. Nah. And I wonder where they got their name. Let's see if I can find something real quick on the internet. I can't find a name. What is orthos? Various pharmaceutical products. Anyways, I'm sure I know how they got their name from orthos substituted benzene rings. All right, it's practice time. And let me remind you, at least I'm having a somewhat decent ring drawing day. This is benzene, 3 possibilities how to draw it. This is toluene, 3 ways. And finally, let me remind you, ortho is 1, 2, meta is 1, 3, and pair is 1, 4. So the question is, all right, everybody, what's the name of that? Time's up. Hopefully all picked benzene. And there you go. And your turn. What's the Iupac name for that molecule? Hopefully you've learned your alkyl groups. All right, I think everybody's done. Let's do it. What do I have? Ooh, a ring. But it's not cyclohexane. It's got stuff inside. That's a benzene ring. See, it says it right here. And what do we have here? 4 carbons, 3 to the center carbon. That's the tert-butyl group. But I'm going to start becoming like I am, a lazy organic chemist. I'll call it a T-butyl group. You put down tert, which is short for tertiary. That's fine. I'll put C over here. And why don't you try that one? Give the Iupac name for the following. And don't forget, lab is due tomorrow. And I'd like to thank everybody for handing in the lab. It made me very happy. All right, I think everybody's done. If we look at C, oh, I've got a benzene ring here. Up here, I have an ethyl group, and 3 carbons to the center carbon is called isopropyl. And hopefully, ASAP, you've learned the alkyl groups on the table I gave you. So the name of this would be ethyl isopropyl. Bad habit of Dr. White. You can do a capital I, but I really shouldn't. Now, we're not done. Where's the ethyl and isopropyl? 1, 2, 3, 4. If you started from here, 1, go the other way, you get the 4. So what's a 1,4 disubstituted benzene ring? para. So this would be para ethyl isopropyl benzene. And what would be the name of that compound? I'll give you 10.6 seconds. Go. Well, I gave you more than 10.6. Benzene ring with a methyl, toluene. All right, let me put this up. All right, ortho is 1, 2, meta is 1, 3, para is 1, 4. And it's your turn to give the Iupac name for the following molecule in E. Remember, I try and give everybody time to finish. Ooh, excuse me. My body is telling me I'm not used to 3 hours in the morning, 3 hours in the afternoon of lecturing. I haven't lost my voice. That's a good thing. All right, I think everybody's done, so let's get to it. What do we have? Ooh, we've got a ring with conjugated 3 double bonds. Conjugated means alternating double, single, double, single, double, single. And it's got a methyl group on it, and we call that toluene. If this is the 1 position, this is, in case you forgot, That's called N-butyl group. 4 carbons to the N, N-butyl. So this would be N-butyl methyl toluene. And notice that this is carbon 1, 2, 3. It's 1, 3, and that would be meta. So we have meta N-butyl methyl toluene. Now, if you put down meta methyl N-butyl toluene, I would give you full credit. Now, I'm going to write something on here. You don't have to copy it down. Everybody know what that is? I'll let you think for a little while. Time's up. What is this that I just drew here? It's 1, 2, 3, 4. Well, of course, it's paramedic, which reminds me, oh, bad Dr. White. By the way, paramedic, you can laugh or you can, ooh. I forgot to do another one. I think I did. Someone let me know if I already did this. I might have, but I'll do it again. It's fun. What's that? Opposite side hydrogen, trans. And what's this? It's transparent. Ooh. Ooh. All right, let's continue on before I hurt you. All right, now, here's some new substituents, which I'm going to ask you to learn. And we'll talk more about it throughout the semester. Switch, I've just turned to on. You should know this. And let's look. When you have a chlorine on something like a benzene ring or even an alkyl group or alkyl chain, we call that a chloro substituent. Bromine is called bromo. Iodo, iodine called iodo. Fluoro for fluorine. And here's one we haven't talked about, NO2, where nitrogens are attached to nitrogen, oxygens are attached to nitrogen, and this nitrogen is bonded to the benzene ring. That's called the nitro group. Now I have one here. And that's sulfonic group. I'm not going to ask you to learn that, but I will talk about it later on because that's important in how we make our laundry detergent. Whoa, really? Yes, really. And as you've seen already, the alkyl groups are named for the common names methyl, ethyl, etc. So let's take a look at this. What's the name of that compound? Oh, we've got a benzene ring. Cl is chlorine. So this would be chloro benzene. When there's only one alkyl group or substituent on a ring, you don't need a number. All right, why don't you write this down? Then I'm going to show you that slide again. And why don't you use this to help you name that compound? All right, let's do this. What do we have here? A benzene ring. What's this iodine? That's called iodo group. So this would be iodo benzene. All right, let's look. We have two groups on a ring. Use ortho, meta, and para. And why don't I do this one? What is this? Bromo. What is this? Nitro. And notice I have a benzene ring. It's 1, 2, 3 disubstituted. So I have bromo, nitro, benzene. Because it's 1, 3 disubstituted, this would be meta. That came off in left field. Metabromonitrobenzene. And why don't you try this one? Cl is chloro. I'll help you out. NO2 is nitro. And 1, 4, in case you forgot. There you go. 1, 2 ortho, 1, 3 meta, 1, 4 pure. Going a little into our break. I won't cheat you out of your break time. Aren't I nice? I guess proper English. Am I not nice? All right, let's give it a go. And we have what's here? Oh, a benzene ring. And we have a nitro group and a chloro group. You haven't learned that table yet. I would start as soon as possible learning that. Nitro, and notice 1, 2, 3, 4. And what's 1,4 disubstituted benzene? It's called para. So this is 1,4. Therefore, this is para chloronitrobenzene. If I look at the clock, I went a little over than I expected. And because that, I'm going to give you a long break. Let's come back at 3:55. Come back at 3:55 and we will continue. Remember, I'm going to end. If you want to stick around, I'll teach you the method, how to eliminate test anxiety. All right, I'll see you back in about 5 or so. Time to get going again. And let me remind you, today at about 3:30, I'm still on spring semester mindset, which starts at 1, not 2. At 4:30, I'm going to stop class, but I'm not going to stop here. At 4:30 today, I will go through the method, how to eliminate test anxiety for anyone who wants to stick around. I will cut it out of videotape, but if you're not able to come here and you're watching this videotape, you can come to my office hours or come to make arrangements, and I'll meet you on Zoom sometime convenient for both of us. Speaking about that, I'm toying with an idea, which I think I'll do over the next couple of weeks. I'm going to ask to arrange Zoom meetings with each of you individually so you can feel comfortable. I won't record it. And turn on your webcam and I get to know you a little, because all I see right now is me, which I know, and names on the screen up above. Turn on your webcam. Make Dr. White happy. No, you don't have to. All right, we're talking about nomenclature of aromatic compounds. Let's do one more. I'm going to let you do this one all on your own, but I'll help you out. Remember, NO2 is called the nitro group. And what would be the Iupac name of that molecule? Remember tomorrow, the lab we did last week, distillation is due, and I already have set up on D2L both of the labs this week. That way I don't have to worry, did I forget to do it? Which I didn't. And in case you forgot, 1,2 is ortho disubstituted for only benzene ring. One, and that includes toluene. 1,3 is meta, 1,4 para. 1,2 ortho, 1,3 meta, 1,4 para. All right, while you're doing that, I'm going to ask you to do a favor for Dr. White. And that is with your thumbs up emoji. Right now, instead of putting the big ceiling fan I have up here, which causes some reflections and light in the room on Zoom, I have a tiny little fan behind me, even though my air conditioning is doing quite well. Thank you. But anyways, if you can hear the fan, give me a thumbs up. It's a tiny, small fan. Real nice one I got on Amazon. And it's not USB, it's 120 plug into the wall. It's only about this big. Well, I guess nobody can hear it. Good. If ever I'm doing something, you hear background noise and it's bothering you, let me know and I'll see if I can eliminate it. All right, it looks like everybody's done, so I better get to work. What do we have here? A benzene ring. That's because you see the double bonds inside, alternating double, single, double, single, double, single. But it also has a methyl group. Immediately, that's toluene. And, oh, I've got a nitro group, but I told you that. Be sure to start learning that chart for test number 1. And notice this is 1,2 disubstituted. 1,2 disubstituted is ortho. So this would be ortho nitrotoluene. Now, when you have more than 2 substituents on a benzene ring, including toluene, you use numbers. And since it's straightforward, I'll just give you one example. I'll do myself. That looks better. All right, question is, what's the Iupac name of this compound? Oh, I've got a benzene ring, but it's got a methyl group. Immediately I have toluene. It's got not 1, not 2, but 3 nitro groups. Remember, di means 2 groups that are the same. Tri means 3 groups. And therefore, this is tri-nitrotoluene. Now, since we have, in this case, the methyl group is considered a group, 4 groups on that benzene ring, we need numbers. In toluene, that's 1. This is 2, 3, 4, 5, 6. What carbons on the ring are the nitro groups? The answer is 2, 4, 6. So when you see tri, you'll need 3 numbers, 2, 4, 6. So that's 2, 4, 6 trinitrotoluene. 2, 4, 6 trinitrotoluene. Oh no, 2, 4, 6 trinitrotoluene. My jaw's getting tired. You know, organic chemists are lazy. What if it's, well, there's a T here, N here, and just for a common name, what if I call this TNT? And a product made with TNT is dynamite. And this is a structure of TNT, the explosive used to make dynamite, 2,4,6 trinitrotoluene. Now it's time for Dr. White's story. How many of you, and give me a raise your hand, you can use your emoji. How many of you have heard of the Nobel Prizes? I see the hands are starting to come in for those who'd like to raise their hand. And the Nobel Prizes are given for various things. Chemistry is one of them. And who started that? Alfred Nobel. Now, where did Alfred Nobel get all his money to do that? Well, he and his brother found a way of stabilizing trinitrotoluene, 2,4,6 trinitrotoluene. If we were in a classroom and I had this much, or better yet, if this is, and it's not, trinitrotoluene, I slammed it onto my hand, we'd be gone. It'd blow up and we'd be gone. Trinitrotoluene is very shock sensitive. I've never worked with it, nor do I want to. Well, sad story. Even when they found out by mixing, I think, clay with trinitrotoluene to make sticks, dynamite, use a blasting cap to make it go boom. I like that special effect, boom. And when they were making it, it was very hazardous. And unfortunately, one of their plants blew up and it killed Alfred Nobel's brother. And because of that or other reasons, he started Nobel Prizes. Now, where did he get the money? How did he become very rich from finding out how to stabilize a very dangerous explosive, 2,4,6 trinitrotoluene? Well, some of it went to making dynamite for mining, but the bulk of it went to make explosives to sell to militaries of the world for wars. And is there anything wrong with that? Well, in my mind, no. He was just being a businessman, having wars, and why they're, that's another thing, has nothing to do with him personally. So all the money behind the Nobel Prizes, such as even the Peace Prize, come from explosives used by militaries in the world. Interesting. I bet you didn't know that. All right. In nomenclature, there are two types of nomenclature skill. One is, here's the molecule, give the Iupac name. The other is, here's the Iupac name, draw the molecule. And before we go any further, let me do a couple things. It's called preventative medicine, or not medicine. You know how my machine sometimes, and because of the pandemic, I'm having to wait to get memory. Well, all right, let's do the following. And I'll let you try these first. Draw the structure of benzene and toluene. Ooh, it said 2 for Monday. Actually, I should have waited for tomorrow, 2 for Tuesday, but I didn't. All right, I think everybody's done. So let's do this. And what's the structure for benzene? Six-membered ring with double bonds, three of them alternating, single, double, single, double, single, double. You could draw it that way, or this resonance form, or the delocalized pi. Now, toluene tells you there's a methyl group on a benzene ring. Remember, before I do toluene, if you had put this down, that's wrong. That's cyclohexane, and I'd give you 0 points on a test. Please don't do that. Now, toluene is a benzene ring with a methyl group. Oops. So used to drawing the bonds in, because I think it looks cool. I rarely do this. All right, now, how do you draw this one? I'll do this one. As all organic molecules, you start from the right, move left. And oh, benzene. Don't forget to put the bonds in. Common mistake on test one, you'll lose a lot of points if you don't. All right, so on a benzene ring, I have an N-propyl and an ethyl, and it's para. And para is 1,4, meta 1,3, ortho 1,2. So it doesn't matter what you put on top. I'm going to put the ethyl first. And whether you count clockwise or counterclockwise, the para is there, N-propyl, 3 carbons. And don't forget there's 4 bonds to carbons. I know the hydrogens to put in. And that's how you do it. Let me give you time in case, oops. Somebody should have caught me there. All right, let me give you one to try. How did you two get down there? Don't know. This whiteboard sometimes is haunted. Not really. All right, why don't you draw the structure for meta-chlorotoluene? Remember, ortho 1,2, meta 1,3, para 1,4. All right, looks like everybody's done, so I'm gonna get to work. And we start this way. Oh, toluene. That's a benzene ring with double bonds or circle. I'm not going to draw all the different resonance forms. And it has a chlorine. Chloro is chlorine. And where is it? 1, 3. So this is 1, that's 2, that's 3. Now you could have put the chlorine on top and the methyl group over here. Another way of drawing the same molecule, all I'm doing is rotating it like this. Don't forget to put the double bonds in. These two are identical. All I've done is rotate it on a piece of paper. And that's how you do nomenclature for aromatic compounds. One of the things I forgot to mention, but in the lab we'll do Thursday, you'll learn about it, but I'll mention it now. And that is, where some neat places to find aromatic compounds. Well, vanillin, which is extracted in vanilla extract from the vanilla beans. Dr. White loves the good stuff. Anyways, that's aromatic compound. Now, another one, which I like, but my older sister doesn't like, well, but anyways, don't tell her I did that. But anyways, that's cinnamon. You know how you use cinnamon? I like to make cinnamon toast or other things with cinnamon. By the way, cinnamon and apples go, oh, that's so good. But anyways, cinnamon has a benzene ring in it. It's an aromatic compound. And we'll learn more about these structures on Thursday. All right, let's talk about the resonance energy of benzene. Switch is off. This will not be on a test, but it's some background information to help you understand what will be on the test. Now, it turns out, if you think about benzene, it's got 3 double bonds. And you learn, if I take hydrogen, a catalyst, I can break the pi bond, and guess what? I can add hydrogen to each one. Well, if you had cyclohexene, it's not that hard. You can knock it off in a couple hours at 140 degrees. Dr. White knows this stuff. I've worked in those. But benzene to hydrogenate, oh, you really got to go to very high temperature and very, very, very long times. It's really hard to hydrogenate it. Why is that? Resonance energy. And what do we mean by that? Well, benzene does not react like you would expect if you had a separate 3 double bonds. Something's different in benzene and all aromatic compounds, which is what makes them much more stable. And that's called stabilization energy. I like the older name, resonance energy. Again, switches off. Will this be on a test? No, but it's good background information. The energy, difference in the energy of a real molecule and calculated energy for the most contributing structures, that difference is the resonance. If you were to calculate the energy of a cyclohexane ring and a double bond, and since there are 3 of them in benzene, you multiply that by 3, add them together, that should be the energy of a benzene ring. But if you actually calculate it, it's a lot lower. Lower meaning more stable. What's that? Because of resonance. And what we really mean is, don't get dizzy while I'm going back. Right here, I have my benzene ring. And I've got my 3 double bonds, but in reality, all the p orbital electrons are holding hands to form this pi orbitals or bonds, and it's sort of like in a ring holding hands. And when you break that ring, you've lost a lot of stabilization or resonance energy. Therefore, benzene in its chemical reactions does not want to break the double bonds. And that's an important feature of the chemistry of aromatic compounds. And now, oh, I forgot to tell you something. In my class, you're going to learn a lot of neat words that you can impress your friends, neighbors, and loved ones with. And now is the time to learn some neat words. Now, benzene, the double bonds in benzene do not undergo addition reactions because that would break the double bonds. What they do undergo is called electrophilic aromatic substitution. What does that mean? Well, substitution, you change one thing for another. Aromatic, you're dealing with something like a benzene ring. What's that electrophilic? Well, electro comes from the negative charge of electrons. And philic comes from the Latin, I think, phile. And this means lover. An electrophile is something that loves electrons. And I can tell you honestly, I'm an audiophile. And what's an audiophile? I like my music, all types of music. Did I tell you I saw Jimi Hendrix live when I was in high school? I did. Oh, greatest concert in the world I've ever been to in my life. And I've seen some good bands play, including once when they were practicing before our concert here in Chicago, I saw Led Zeppelin in a small bar on the north side of the city. Wow, that was great too, but it didn't compare to Jimi Hendrix. Wow. But anyways, I'm an audiophile. Audio, sound, music, phile, lover. So electrophiles are molecules or parts of molecule that love electrons, meaning they're looking, where's an electron? I want an electron. So let's look at the first reaction. And the first reaction is called halogenation. Now, unlike halogenation of a double or triple bond, this is a substitution reaction. And here you take halogen gas, and you need a catalyst for this. And the catalyst for this reaction is ferric trihalide. And that reacts with the gas to form an electrophile. Now, in reality, the only halogens that are used for this reaction are chlorine or bromine that I know of. Now, you also replace one of the hydrogens with X, and you're left over with another X, and you get HX. Now, HX, like hydrochloric or hydrobromic, is inorganic, and I'm a biased organic chemist, so I don't care about that, because on a test, I'm going to ask you, give the product or products for the following reaction. So let's look at this. Oops, wrong thing. And again, the question is, give the organic product or product. If you feel you need to put down the inorganic, that's fine with me. But if you don't, I'm not going to mark it wrong for the inorganic. Now, if we look at this, what's the general reaction you need to know? Remember, this is the roadmap that helps you find out where are we going, or in this case, what are you making? And here, take a benzene ring, aromatic compound, and react it with halogen gas, where X is chlorine or bromine for this class, and ferric trihalide. Again, here's what X is. And you replace one of the hydrogens. There's a hydrogen there. We just don't show it with a halogen. And what's X? In this case, bromine. Don't forget to put the bonds in there. If you don't, that's cyclohexane, and I'll mark it wrong. That's why that student lost 10 points. And you get bromobenzene. Your turn. Now it's your turn. Sorry about that. And what would be the organic product or product for the following? And look above. All right, my turn. And what do we have here? What's, oh, a benzene ring, halogen, chlorine, and ferric trihalide. And here's the general reaction you should know when you have a benzene ring reacting with halogen gas and ferric trihalide. Replace one of the hydrogens with a halogen. Remember, I'm asking give the organic product or products, and HX is inorganic. So what's X? Chlorine. Don't forget the bonds or circle, because if you did, if you were to write this, It's wrong. That's chlorocyclohexane, and you should have written chlorobenzene. So don't forget, either put a circle or the bonds. All right, as I look at the clock, I went a little longer, but we still got plenty of time. And what I'm going to do now is I'm going to do a goodbye. Hold on, don't leave yet. I'm going to do an official goodbye, and then I'm going to start immediately, for those who want to stick around, teaching the method how to eliminate test anxiety, but I'll cut that out of the video. If you are watching the video not with us today, you need to learn how to do that or want to learn how to do that, either come to my office hour, I'll teach it then, or make arrangements and I'll get together with you. All right, I'm going to sign off officially, and then stick around if you want to learn the methods. And with that, I'll say, Gehen gesund, goodbye.